Hello everyone. So let me start my third lecture on acid-base chemistry, where the fifth concept on acidity and basicity, which is the Lewis acid-base theory, will be discussed. Earlier we have studied four acid-base theories: Arrhenius, the Franklin solvent, the Bronsted-Lowry, and the Lux-Flood concept. This Lewis acid-base theory is also known as the electronic theory. This theory is based on the electron pair acceptance and electron pair recepting. That means earlier we have studied that acidity and basicity can be described on the basis of proton acceptance or proton donation, oxide acceptance, oxide donation. Likewise, here this is much more advanced theory, where an electron pair acceptor will be considered as an acid, which is called a Lewis acid, and an electron pair donor will be considered as a base, which is a Lewis base. Now the salient features of this theory are, first of all, the base has lone pair of electrons and the acid possesses an empty orbital which may accommodate a pair of electrons. So to donate a substance which has a lone pair of electrons which they can donate, if so, then it will be treated as a base. And if a species has to accept a lone pair, then it should have the accommodation facility so that it can accommodate the accepted electrons in the way so that it has some empty orbitals. Secondly, it includes the reactions in which no ions are formed and no hydrogen ions or other ions are transferred, such as in the previous examples, H plus ions, OH minus ions, or oxides. Sometimes these ions were involved, but here in the Lewis acid-base theory, the involvement of ions are not here. And thirdly, after the electron pair donation and acceptance, a coordinate covalent bond is formed. Actually, coordinate covalent bond is a type of covalent bond which is the primitive stage of formation of a ionic bond. Ionic bond means a covalent bond with high polarity, with a positive end and a negative end. So this coordinate covalent bond is formed in case of an acid-base reaction. So we have to throw more light on this theory with some examples. In the first example of Lewis acid, in these examples the molecules should contain such an atom which has incomplete valence shell. Here we have two examples of Lewis acids, which are, first it is barium trichloride, and secondly it was aluminum trichloride. So barium, I'm sorry, this is boron trichloride and this is aluminum trichloride. So boron trichloride has 6 electrons in its valence shell. Actually it is owner of 3 electrons, and from 3 bond pairs it has 3 valence electrons, 6 valence electrons. So it is deficient of 2 valence electrons to complete its octet. So it has an empty orbital. So this orbital is ready to accept the electron. So this is the Lewis base, ammonia. It will form an adduct like this. This is the coordinate covalent bond. Finally, actually the bond is the covalent bond, where this bond is highly polarized, where nitrogen end is positively charged, on the other hand the boron end is negatively charged. And in the second example, aluminum trichloride reacts with chloride ion. Chloride has 8 electrons, 4 pairs of electrons, which is a Lewis base. So this electron, when donated to the aluminum trichloride in the empty orbitals of aluminum, accepts this pair of electron, and this aluminum tetrachloride negative ion is formed. In the second example, the cations with a suitable and low-lying orbitals, which is empty or partially filled. So the cations are Lewis acids which has low-lying orbitals, which has stable low-lying orbitals. Silver ion, it has 5s1 configuration, now it is 5s0. Hydrogen, 1s1 electron, now it is 1s0. So they are all Lewis acids. All they can react with Lewis bases like ammonia, H2O. Here with ammonia, it reacts with 4 ammonia molecules, and finally it forms this square planar complex, tetramine silver plus. On the other hand, ammonium ion is formed from this Lewis acid base reaction, and hydroxonium ion is formed from this Lewis acid base reaction. And in the third example, we have the compounds with double bonds other than C double bond C. Here the double bond is C double bond C, but here the double bond is C double bond O. This carbon is highly deficient of electrons because they are connected with 2 oxygens. They are attached with 2 oxygens, where oxygens are highly electronegative, so they are pulling the electrons towards themselves, and this carbon becomes highly susceptible to accept a nucleophile. Here the electrophile nucleophile reaction can also be explained on the basis of the Lewis acid base theory. Here the hydroxyl ion is playing the role of a Lewis base, but actually this is a nucleophile, and this is becoming an electrophile. So when an electrophile reacts with a nucleophile, this is also a Lewis acid base reaction, and this bicarbonate ion is formed. Now we move on to the example of the Lewis bases. The molecules having an atom with 2 or less unshared pair of electrons are Lewis bases. Now if the unshared electrons, number of unshared electrons increase, then the basicity decrease, and in case of ammonia to water to hydrogen fluoride to neon, here we find that the number of lone pair of electrons increases from a single pair to double pair to triple pair to 4 pairs. So highest basic among all of them is ammonia, because it has the least number of lone pair. On the other hand, neon has 4 electron pairs, so it has no basicity. HF is also a base because of having 3 pair of electrons. Here is the example where HF is a base when it reacts with sulfur trioxide, so it plays the role of a base. It reacts with sulfur trioxide to form HSO3F. In the second example of Lewis bases, in the arena of the anions or the negatively charged ions, almost all negatively charged ions are Lewis bases. They can easily react with Lewis acids. This example is known. Earlier we have cited this example, chloride with aluminum trichloride to form aluminum tetrachloride negative ion, and when fluoride ion reacts with BF3, then BF4 negative ion is formed. Now this third example, in this example 2, this subcategory third example is most important. This is important on the basis of your practical of your practical experiments in the lab. In general, iodine does not dissolve in water, or iodine is sparingly soluble in water. But if you add a pinch of potassium iodide, then it becomes completely soluble. Why? That is a question. So iodine actually reacts with iodide ion to form triiodide. Here this is also a Lewis acid base reaction, where iodide is a Lewis base and iodine is a Lewis acid. It can accept a lone pair of electrons because it has empty d orbitals. These empty d orbitals can easily accommodate the lone pair of this iodide ion to form the triiodide ion. Triiodide, T-R-I-I-O-D-I-D-E, triiodide ion. So the reaction is Ki plus I2 equal to Ki3. In the equilibrium constant determination, practical chemistry, we use this reaction. Now in the third type of example, the pi acid ligand is the most important and interesting example. Now we have learned that carbon double bond oxygen, this is a Lewis acid. Now actually the metals are the pi electron acceptors. This is the metal M, which has empty d orbital. so they can accept the pi electrons from the olefinic C double bond C, or in benzene also they can react. The question is that the substances like BF3, AlBr3, AgClO3 all are highly soluble in olefinic compounds or in the benzene derivatives. Why? So the answer is the central metals like boron, aluminium and silver, they are very good pi electron acceptors. Now how they react with the olefinic pi electrons? The olefinic pi electrons can be of two types according to their symmetry. This is symmetric, this blue carbon double bond carbon is symmetric, and this is asymmetric. That means this can form the pi electron, and this can form the pi star electrons, or the pi cloud is here simply pi and here pi star, okay, in the excited state. Now both can combine with the empty orbital of a metal. If it is pi, then it can react with the empty d orbital like this, or if it is pi star, then it can react with the filled d orbital like this. So here sigma bond is formed as a result, and here the pi back bond is formed as a result. So this is the most beautiful area where the Lewis acidity and basicity has high acceptability. So what is written here? The donation of an electron pair from a pi bond to a Lewis acid like a metal ion BF3, AlBr3, etc. results in pi complexes. In a number of complex compounds of ethylene with silver, platinum, rhodium, it has been definitely established that the metal atoms are bonded not to any single carbon atom but to the pi bond directly. The high solubilities of Lewis acids like BF3, AlBr3, AgClO4, etc. in benzene derivatives and in olefinic compounds also involve acid-base interaction involving the pi bonds. Now, the speciality of the Lewis concepts, not only this is covering a wide area, it has few special features which is very much unique rather than the other theories of acidity and basicity. The first of all, it is the Lewis concept covers the Bronsted-Lowry acids and bases, most of the bases, and at the same time includes the non-protonic substances. That means the area of Lewis acids and bases are much wider here. The Lewis acids and bases can be titrated to an endpoint using colored indicator. So not only Arrhenius acid or a Bronsted-Lowry acid can be titrated with the help of an indicator, the Lewis acids and bases can also be titrated with the help of an indicator, colored indicator. The inclusion of complex formation by metals is another interesting feature of the concept, as in the third example of the bases, the organometallic formation of organic metallic compounds, or the metal compounds, the solubility of the metal compounds in benzenes or the olefinic benzene derivatives or the olefinic compounds was very much well explained by this theory. Simultaneously, the Lewis concept introduces a parallelism between acid-base character and redox power of a substance. So here is the another very good feature of this theory. That means Lewis acids are electron acceptors. That means they are oxidizing agents. On the other hand, Lewis bases are electron donors. That means they are reducing agents. So the redox characteristics can be synchronized with these Lewis acid base characteristics. As for example, a strong base being a good donor of an electron pair would be a strong reducing agent, and vice versa. Now, every theory has some limitations. So this theory, from the hardcore thoughts, this theory also has some demerits. What are the demerits? First of all, listen carefully. The conventional protonic acids like sulfuric acid and hydrochloric acid are not covered directly by this approach, as they do not apparently establish a covalent bond by accepting a pair of electrons which a Lewis acid ought to. A compromise can be done by assuming that hydrogen bond is first formed in reaction of an acid HX and a base B as X bond H, hydrogen bond dotted line B. This undergoes fission to give the neutralization point. So if some acid, a bronzosylate acid, releases some proton, then where is the electron pair acceptance? So this was compromised by this theory. That means before donation of the H plus ion, actually the hydrogen bond is formed with the base. Okay, now this bond pair is accepted by this X, that means the halogen. Okay, then the H is released by H as H plus. So this way we have adjusted the Lewis theory with the protonic theory. Now the next one is the Lewis approach lies in ascertaining relative acid base strengths. Now in the relative acidity and basicity, sometimes some anomalous things develop here. Here the acidic or basic strength of a species is dependent on the nature of the reaction studied and not on the absolute power of accepting or donating a pair of electrons. So there is some ambiguity there. Does the fluoride complex, now look at the examples here. Does the fluoride complex of beryllium 2 is more stable than the corresponding complex copper? Now this suggests that beryllium is strong Lewis acid than copper, but the amine complex of copper is far more stable than that of beryllium, suggesting the copper is a stronger Lewis base. So this ambiguity cannot be explained on the basis of Lewis acidity and basicity theory. There are some more demerits of this concept. One of the starting points of Lewis approach was that the acid-base reactions should be fast. So in general, all acid-base reactions are fast, but some Lewis acid-base reactions are slow. But this is not in practice for many reactions due to kinetic factor, although they definitely involve acids and bases. For example, the formation of this hexamine chromium complex. So this is a slow reaction. Okay, but according to Lewis base acidity theory, some acid-base reaction is taking place here, but slowly. Okay, so not necessarily all the reactions should have to be faster. The catalytic activities of acids and bases, one of the preliminary considerations by Lewis, are not in harmony between the protonic acids and Lewis acids. The reactions catalyzed by Lewis acids are generally not catalyzed by the protonic acids. So in our biological systems particularly, so many catalytic activities are involved. Now if some protonic acids do some catalytic activity in our biological system or in some other sophisticated systems, but similar activities will not be performed by some Lewis acids. So these are another demerits of the Lewis acidity and basicity. So that's all about the demerits of Lewis acidity and basicity and overall theory of the Lewis acidity and basicity. Thank you.